All right, everyone should have your notes in front of you. If you didn't finish your Desmos, just keep the tab open and you can finish it when you have a moment of downtime. Make sure you have a pencil and you're looking at your notes. All right, I'm going to try to read from my screen because it's really tiny. The parent function for exponential decay functions. Remember, you saw a function like this when you were doing the area. The area was getting smaller and smaller exponentially. And then here's your parent function for exponential growth functions. Notice that the difference is when it's growing, then the base, that's that b number underneath the x, that's going to be a number that makes things larger. So like multiplying by 2 made things larger, and so that b number was a number bigger than 1. Multiplying by 2 makes things bigger. When it's decay, when it's getting smaller like this, your base is going to be a number that is less than 1, like a fraction. It could be 1/2, 0.5, 1/3. Those numbers will make it go smaller, and that will give you a decay function. So it says, what kind of function is created when b is between 0 and 1? Just like we saw with the area getting smaller, the function was decay. Decay. And if your base is larger than 1, then you're going to keep multiplying and making something bigger, and that's growth. All right. Look at A and B below. And I want you to decide if it is growth or decay. And the growth or decay factor and its rate. And actually, I think I'll need to get into those things with you in a minute. But start by just looking at A and B to determine if they're growth or decay. One person said decay. Anybody else say decay for A? Good. So A is decay because 2/3 is less than 1. Okay? So if that base below the x is less than 1, it's going to be decay. Then it asks you for the growth and decay factor, and that's just going to be that 2/3. But the rate is going to be the difference between the factor and 1. So it's going to either be 1 minus 2/3 or 2/3 minus 1, whichever is going to give you a positive answer. So the rate is 1 minus 2/3. I want you to take a moment and talk to your neighbor about what is 1 minus 2/3 without Desmos. What is 1 minus 2/3? All right, raise your hand if you've got it. 1 minus 2/3. What do we get, Andrea? Andrea says 1/3. Raise your hand if you agree. Okay, good. So when you think about thirds, and guys, I understand that this is an elementary topic, but it's also a topic that many adults do not have a grasp on, and so I just want to make sure that you guys are mathematically literate. So if you have a whole and it is split into thirds, and you want to subtract out 2 of the thirds, you will have 1/3 left, okay? One way you can do it is to change the number 1 to 3/3. 1 is the same as 3/3. 3/3 minus 2/3 is 1/3. Another is just to picture it. In the whole, there are 3/3. You subtract 2 of them, and you are left with 1/3. So the rate is 1/3. So go ahead now and do B. I want you to tell me if it's growth or decay, what the factor is, and what the rate is. The rate will always be positive. So even if you get a negative, just make it positive. All right, B, is it growth or decay? It is growth, good, because even though this is a fraction, 3/2 is bigger than 1. It's 1.5, right? So multiplying something by 1.5 will make it bigger. So this is a growth. Whoa, growth. Because 3/2 is greater than 1. And the factor is just 3/2. But did you guys find the rate? Okay, so the rate is going to be a rate it's increasing by, and it's increasing by 50% each time. So it's just the 0.5, but you can do that by, it's the difference between this number and 1. So the rate is 3/2 minus 1, which is 1/2. Now, I know that we did this backwards before, right? It's just because we want a positive answer for our rate. So this one is decreasing by 1/3 each time, and this one is increasing by 1/2 each time, okay? If you get a negative number, just make it positive. There aren't going to be any negatives in exponential growth and decay. All right, C is tricky. Let's look at C. What's different about C? There is a whole number in front. Oh, there's a whole number for the base, true. Mm-hmm. There's a negative exponent. Do you guys remember what a negative exponent does? Let's see. A negative exponent takes the reciprocal. So a negative exponent gives the reciprocal of the base. So this is really f of x equals 10 times 1/3 to the x. Oops, you can't see any of that. Let me see if I can move this. There we go. When you have a negative exponent, it gives the reciprocal of the base. So it's really f of x equals 10 times 1/3 to the x. So that means that this one is growth or decay?
Decay.
It's decay because 1/3 is less than 1. Decay. The factor is how much?
1/3.
The factor is 1/3. And then the rate is 1 minus 1/3, which is what? It's 2/3. Remember, here's my picture of thirds. So if I wanted to subtract out just one of them, I would be left with 2/3. All right, do D.
Even though the
So to do D, you notice that the base was 0.25, and we had to do the reciprocal of 0.25. What is the reciprocal of 0.25?
4.
It is 4. How did you know that?
Because 0.25 is 1/4.
It's 1/4? It is, 0.25 is 1/4. Now say, for some reason, that just doesn't occur to me. You could also just use Desmos, and you could do 1/0.25, and it will give you 4. But most of you were thinking, oh yeah, that's 1/4, so that's going to be 5 times 4 to the x. And so then, it's growth or decay? Growth. And your factor is 4. And what's your rate? It's always going to be positive, so it's what? 4 minus 1, which is 3. Good. All right, any questions on that? Okay, we are going to need Desmos for the next part, because we're going to be graphing. So open up a new Desmos. Okay. All right, exponential regression is going to give you an exponential equation that fits a set of data. We're going to actually be doing this later for our project in this unit, but for now we're just doing it in our notes. So 3 kinds of regression that we've learned about are linear, quadratic, and exponential. If your graph makes a linear shape, you might do a linear regression. If it makes a quadratic shape, which could be a parabola that opens up or a parabola that opens down, then it could be a quadratic regression. And if your data makes an exponential shape, either exponential growth or exponential decay, it's going to be an exponential shape. So to do these problems, sometimes they tell you what kind of regression to do, and sometimes you need to reason it out. A cup of soup is left on a countertop to cool. The table gives the temperature in degrees Fahrenheit of the soup recorded over a 10-minute period. Using an exponential model, so they told us what to use, write an equation for the curve of best fit, and then estimate the temperature for 5 minutes. So I need you guys to add this table into Desmos. So you get a table by hitting the plus, add item, add a table, and then you're going to enter those points. When we write the equation, we don't write this way that we talked to Desmos, y1, x1. We're writing a normal equation with y and x. The format of the equation is going to be y equals a times b to the x. And what we're going to do is we're going to use the a and b numbers that we just found in Desmos. So I'm going to go back and get those numbers from Desmos. I'm going to write on my paper and then I'll share that with you. Y equals, instead of A, I'm putting 180.325. And then times, I'm going to use 3 decimal places, 0.954 to the X. So, this is the format for your equation. This is using the A and B values that we just found in Desmos. And now it says to estimate the temperature for 5 minutes. Is 5 minutes an X or a Y value? Thank you. 5 minutes is an X value, so we're going to put 5 in for X. So we're going to say Y equals 180.325 times 0.954 to the 5th power. We're going to put that in Desmos, and we're going to see what we get. What would be the temperature? Okay, so I'm getting about 142.5 degrees. Did you guys get that? About 142.5 degrees? All right, so in problem 2, we use the years since 1992 in your X, and then we put the NASDAQ in your Y there. And when you do your regression this time, take a look at the top of your table. I have X1 and Y1 at the top of my table. Raise your hand if you also have X1 and Y1 at the top of your table. Okay, good. Put your hand down. Raise your hand if the top of your table says X2 and Y2. Anybody have X2 and Y2 at the top of their table?
Yeah.
Yeah. So when you do your regression, you have to match your table. Mine has X1 and Y1, so I'm going to type the same thing I typed last time. But if I had X2 and Y2, I would need to switch them. So if this says X2 and Y2, then down here, use X2 and Y2. You're telling Desmos to take the information from this table. And so if you did it correctly, you should get the same A and B values I got. I have 242.633 and I have 1.443. I'm going to round that too. Does anybody have a question about how to get those values? Raise your hand if you have a question. It could be a very easy fix. Okay. So we're going to use these numbers now to write an equation on our paper. So we're going to write, I'm going to write the generic one first, just so I remember. This is what I'm going for. And then instead of A, I'm going to put in my A number, and instead of B, I'm going to put my B number. Let's see, I'm going to use 3 decimal places. So 242.633. And then times 1.44, and I'm going to round that 2 up to a 3. If you want to write 1.4429, that's okay. And then raise to the x. All right, then it says estimate the year in which the closing price will reach $9,500. Now, to solve this problem, this time notice we're putting this in for a y value. Y equals $9,500. To solve a problem like this, we would need a logarithm. Have we talked about logarithms yet? No. Okay. So, because I haven't taught you how to solve with logarithms today, we're going to solve this graphically. But on another day, in this unit, we're going to learn about logarithms, and you'll be able to solve it algebraically. Okay? So today, we're going to solve it graphically by putting y equals 9,500 into our graph. So let me zoom fit this. You guys need to also type y equals 9,500. Can you see where the solution to my problem is? Yes. So up here, y equals 9,500. Here is the closing price of the NASDAQ. And so it's going to happen in how many years? Yeah, if you click on that point there, you'll see 9,500 in about 10 years, which we do want to change to a date. Okay? All right, so we put y equals 9,500 in, we put our equation in, and we got x equals 10 years. That's 10 years after what year? What was our start year? So 10 years after 1992, which would be what year? 2002. So that's the year the NASDAQ should have reached 9,500 if it followed this exponential pattern. Okay, so this time it was the number of bacteria present in the culture, and we have hours versus bacteria. It says to round to the 100th place. It's okay if you did that, but I'm going to round to the 1000th place, which is 3 places, just to have a more precise answer. But it's really fine if you follow the directions and you did the 100th. So I'm going to first look at it. So it looks like that. And then I'm going to type in my regression. And now I'm going to write down 3 decimal places for these numbers. Y equals 918.208 times 1.091 to the x. So if you did get a different answer, you might have forgotten to make sure that the y1 and x1 matches the top of the table. Okay, I can check with you then. Or you could have a typo in your table, or I could have a typo in my table. Did I have a typo? I think mine's okay.
Oh, I put the wrong one in the wrong.
Okay. All right. Use the equation to determine the number of bacteria present after 13 hours. And this one I said to the nearest whole number, because when we're counting bacteria, there are no half bacterias, okay? So once we get our equation like this and we put 13 in, the final answer will be rounded to a whole number. So I'm going to do 918.208 times 1.091 to the 13th power, and I'm going to put that into Desmos. All right, so rounding that to a whole bacteria, I get 2,849 bacteria. Did anybody else get that? Raise your hand if you got 2,849 bacteria. Good. Okay. 2,849 bacteria. Okay.